everyone. So welcome to SciSalt's first talk of the academic year. Today we welcome Professor Michael Meredith. Professor Meredith is an oceanographer and a science leader at the British Antarctic Survey and a professional fellow in oceanography at Marriott College. His research centers mainly around polar oceans, famously in understanding the southern oceans and controlling regional and global climate via ocean circulation. In today's talk, Professor Meredith will provide an overview of the changing polar regions and their importance to planet Earth and its inhabitants, drawing on findings from the recent and ongoing research programs and assessments, including the recent IPCC Special Report on the Ocean and Cryosphere. Without further ado, please put your hands together to welcome Professor Meredith.
So hopefully you can hear me. Shout if you can't hear me. Great, no one shouted. Thank you very much for coming along. You've just heard what I'm going to do today is give a talk about climate change primarily, and a particularly polar perspective on climate change, because that's my background. I do polar science, in particular the ocean part of polar science, so you're hearing a lot about that. And I hope you find it interesting. I realise I'm meeting people here for the first time, so some of you are wondering, who is that guy? So to give you a little bit of background, I'm an oceanographer, which means I study the ocean. I'm a practical oceanographer, which means I go to sea on ships and I make measurements, and I try and understand those measurements and try and understand what they tell us about climate change, about the ecosystem, about the future of planet Earth. And I do various other things as well, including being a fellow at Marriott, which is new and exciting for me. So if you want to talk more about these sorts of things, by all means pop along to Marriott, and there's a chance you might find me there, and it'd be lovely to see you. The main focus of the work is the point at the bottom here about science into policy, which is the background of climate change, how we understand it, how it's proceeding, and what we might do about it. So I thought I'd start by showing you this. I'm sure you recognise it. This is home. This is our planet. The reason I'm showing you this is that someone once told me that if you want to grab an audience's attention at the start of the talk, what you have to do is start with a controversial statement. My controversial statement is that the Earth is round. And you might think, well, is that really controversial? Didn't we know that already? And it's a good point. The Earth is actually quite round, not completely round, but it's relatively round. Possibly more surprising is that the Earth is very, very smooth. In fact, the Earth is so smooth that if you shrunk it down to the size of a billiard ball and held it in your hand, it would feel smoother than a billiard ball. So the highest mountain ranges, the deepest ocean depths would all be just a fraction of a millimetre thick in your hand, and you wouldn't be able to feel it. It would feel perfectly smooth. So the question is, if we're interested in the oceans, which I am, why do they matter? If they're just this thin veneer of water that's clinging to a very smooth planet, why do we care about the oceans? Well, that's a very good question. Now I think you can begin to get a perspective on that if you look at a map of planet Earth. Now this isn't a usual sort of map of planet Earth. This is on a very interesting projection. This is called a Spillhouse projection. The normal maps you see are the continents surrounded by water, and what the Spillhouse projection does is actually shows you a map of the world from the sort of fish's perspective. If you asked a fish to draw a map, and they could hold a pen, this is what they would draw. So it's the ocean surrounded by land. And if you draw it in this sort of perspective, what you can see is that there is only one ocean. There's only one of them. They have different basins, the Atlantic, Pacific, the Indian, the Arctic. There's only one of them. So it connects across all the spatial scales of the planet. And you can see that more clearly if you draw a cartoon of ocean circulation on top of this perspective. Don't worry about the details of the arrows. They all show different waters moving in different ways, different depths. But it's this connectivity across the whole spatial scale of the planet. That's one of the reasons that the ocean matters so much. This connectivity, it moves water around, it moves other really important quantities around, like heat, like carbon, like oxygen, and nutrients. We'll come on to those in due course. The key thing you can see though is that the ocean around Antarctica is actually very central to the global ocean circulation. We think of Antarctica being a long way away, bottom end of the planet. In reality, it's absolutely central to what goes on everywhere else on the planet. Because around Antarctica, the ocean unifies the Atlantic and the Pacific and the Indian Oceans. It also is a key place where waters can rise up and take down heat and carbon from the atmosphere and then sink back down into the ocean interior. More than 70% of the ocean, if you look at the global ocean, more than 70% of it was most recently ventilated in the Southern Ocean around Antarctica. That means it was last in contact with the atmosphere close to Antarctica. Why does that matter? Well, for water, seawater, to affect our climate, it has to exchange things with the atmosphere, and that's what the ocean does. It takes down heat from the atmosphere, it takes down carbon from the atmosphere, and that affects climate on a planetary scale. So the heat that gets drawn down into the ocean then doesn't go into the land surface, it doesn't accelerate global warming. The carbon that gets drawn down from the atmosphere, that slows the rate of the greenhouse effect. So you're taking carbon out of the atmosphere where it would accelerate climate change, and you're storing it in the ocean. And the polar regions are absolutely critical for this drawdown of heat from the atmosphere, this drawdown of carbon. You can see the numbers here on the pie charts. Ocean heat uptake, more than 70% of that happens in the ocean around Antarctica. Carbon uptake, not quite as big, but still very, very significant. And the Arctic is also significant in these terms. So the ocean is doing us a really big climatic favour. It's slowing the rate of climate change. If the ocean weren't there doing that, the rates of climate change we'd be exposed to, where we live on land, would be much, much stronger than they are. So how much of a favour is it doing? Well, you can actually put some numbers on it. And this number is a number that I calculated based on UK government figures for carbon credits. So it's just a fun little exercise you can do. But the UK government has issued figures for how much it thinks carbon credits are worth. If you look at the Southern Ocean around Antarctica and calculate how much carbon it draws down, you can come up with a figure for how much of a climate favour it's doing us. And the answer is about £61 billion per year, which is not a small amount of money. Now the key thing is that we can't just take this money and spend it, but it is money that we have to find if we wanted to provide this climate service that the Southern Ocean is doing us in a different way. This sort of number is just for the Southern Ocean. If you look at the global ocean as a whole, if you add in the heat as well, it's many times this. Huge favour, but it comes at a cost. So this climatic favour doesn't come for free. There are penalties associated with that. Those penalties are the ocean is getting warmer. All this heat that goes from the atmosphere into the ocean makes the ocean warmer. That matters. I'll come on to that in a moment. The ocean is also losing oxygen. The ocean is also melting the giant ice sheets. That causes sea level rise. The ocean, because it's drawing down carbon, is acidifying, and that matters as well. I'll come on to all these things in more detail in just a moment, but you can see this big climatic favour that the ocean is doing us is having a real strong negative impact on the ocean itself. So we need some policies. We need to avoid catastrophe climatically, and we also need to avoid catastrophe in terms of damage to the ocean and its ecosystems. So we need some policies, we need some strong decision making from governments, and of course these decisions should be evidence based. Anyone can make a bad decision. If you want to have any chance of making a good one, you need some evidence and make some policies based on that evidence. So who provides that evidence? And the answer is we do, scientists. We can't expect policymakers, we can't expect governments to sit down and read our scientific journal papers. They're very busy people. But what we can do is package the information that we produce, the scientific knowledge about the ocean, about climate change, and give it to the policymakers in forms that they can understand and that they can use for setting their policy. And that's where this organisation comes in, the IPCC. The IPCC is the Intergovernmental Panel on Climate Change, and it's a United Nations body, and it exists to collate all available scientific information about climate change and present it in a way to governments that they can make policy based upon that, to try and avert the worst consequences. I'm involved in IPCC. I was a lead author on this report, which is the Special Report on the Ocean and Cryosphere. It was published a couple of years ago as part of what's called the 6th assessment cycle. These other reports are part of that as well. Why was this report needed? Why did we need a special report on the ocean and the cryosphere? Well, the ocean famously covers 70% of the Earth's surface. The cryosphere, the frozen parts of the planet, cover another 10%. So collectively, that's an awful lot of the ocean's surface covered by ocean or cryosphere. And the part that we live on, ground, is actually quite a small minority. However, the ocean and the cryosphere previously have been underrepresented in the policy dialogue. It wasn't absent completely, but it was underrepresented. And the policymakers themselves said they needed better information and more knowledge about their policy decisions in relation to the ocean, in relation to the cryosphere. So that's what we tried to give them. So where does the evidence that we give to them come from? And the answer is data. We go out and we make measurements, and we understand how the ocean's changing. We understand how the cryosphere is changing. We understand why they're changing as best we can, and we present evidence on that. That's challenging in the polar regions. What this plot shows is the density of measurements of temperature at the surface of the ocean, historically. And you can see all the blues show there's lots and lots of measurements in the North Atlantic, or the North Pacific, or the Northern Indian Ocean. And that's where we know, to quite a high level of certainty, how things are changing. If you go to the Southern Hemisphere, the story is very different. The Southern Hemisphere is quite remote from many of the major population centres of the world. It's a very difficult place to go and make measurements if you want to get right close to Antarctica. You can see down here around Antarctica, these orange colours, that means there's very little data at all, historically. These blue lines you can see, these are trade routes. So ships ply these routes back and forth, and they make measurements as they go, and that measurement helps inform our science. Very few trade routes in the Southern Ocean. There's one or two where people go and resupply Antarctic research stations. A few in this little passage here, but very few. And so there's a real historical sparsity of data and a real bias. That means that historical data is extremely valuable. This pattern is improving. It's getting better. We now have better ways than just ships of making these sorts of measurements. There is still big challenges about making measurements around Antarctica. What other information is needed? Well, measurements can tell you about the past, they can tell you about the present, but by themselves they don't tell you anything about the future. And to predict the future of the Earth, what we need is models. And these are simulations that run on massive computers, massive parallel computers. And if you run them forward, they represent the ocean, they represent the atmosphere, the cryosphere, carbon cycle, the biology. It's hugely complex, but then you can run them forward for 100 years, or 300 years, or 500 years, and they'll give you a prediction of how the Earth is going to change into the future. Now, I'm not a modeller, so this is how I perceive modelling to be. A lot of magic, smoke and mirrors, magic happens, and then a prediction appears, and surely it's got to be correct. In reality, of course, none of them are correct. They're all wrong in some ways, some of them are very wrong, some of them are a little bit wrong. We need to have ways of finding out which the good ones are, because those are the ones we can put more faith in. And that's where the data comes in, and challenge the models with data. How well can they represent the past? If they can do that better, maybe they represent the future better. And the polar regions, even the modelling is very challenging. You don't have to go there to run a model, you just need a big computer. But there's lots of parts of the polar regions that are very, very challenging for models as well. What this plot shows is the circulation around Antarctica. And all these little loops and swirls are eddies in the ocean. These are the equivalent of weather systems in the atmosphere, but they're much, much smaller because they're ocean features. And these loops and swirls have a really big effect on climate, on carbon, all these sorts of things. To represent each of these, you need to have a model that's run with a very, very fine spatial resolution, and that means you need massive computing power. And even today, the state-of-the-art climate models really struggle to include this level of detail. And there's other things as well, like including the ice, including massive ice sheets on Antarctica. This is challenging for the models, but they do a reasonable job. This is a quote I like very much. Nobody believes a model except the person who ran it. Everybody believes a data set except the person who collected it. I'm someone who collects data, so I can certainly confirm that it's true. My wife is a modeler, and she tells me that this bit is true as well. So there's a lot of truth in that asymmetry, I'm afraid. So that's where the information comes from that goes into the IPCC assessments. And I thought what I'd do is just walk you quickly through a few of the key assessment results that have come out recently. And I thought I'd start with the Arctic. The Arctic is very much an icon of climate change. It's changing extremely rapidly. You hear a lot about the Arctic warming twice as fast as the rest of the planet, or 3 times as fast as the rest of the planet. And it's true, it's changing hugely, hugely rapidly. The plot on the right-hand side here shows one of the most well-known manifestations of climate change, and that's the loss of sea ice in the Arctic. And the brown splodge here is the areas where sea ice has retreated very rapidly in the most recent decades. The plot on the left here shows the surface temperature, and you can see that the loss of sea ice is coincident with a very, very strong rise in ocean surface temperature in the Arctic. There's lots of facts and figures in the IPCC reports about this. One of the most striking ones, I think, is that this change of the sea ice is unprecedented for at least 1,000 years, which is a very long time. It's actually probably a lot longer than that even, but this is as far back as we can safely say. And rather depressingly, projected to reach potential, practically ice-free conditions at least once before 2050, under any scenario. And that's important. We do have control at some level about what happens in the future. This change is very strongly linked to climate warming, the greenhouse effect. We can influence how much it changes in the future, but we can't turn it off completely. I'll come back to that. Another change, this is looking forward now. I mentioned before that the ocean is becoming more acidic, and that's a consequence of the amount of carbon that it's drawing down from the atmosphere. It's a simple chemical reaction, it's very well understood. It basically says that the more carbon we put into the atmosphere, the more acidic the oceans become. If we look forward now, you can see how 2 different futures might play out. This is from one of those models that I talked about earlier. That, none of them are perfect, but many of them are useful. And they do all agree that under a low CO2 future, if we can constrain our emissions, the acidification might be comparatively benign. It's not good, but it might be comparatively benign. If we go into a high emissions future, it's a very different picture. And the oceans that are influenced strongest and quickest are the polar oceans, around Antarctica and up in the Arctic. And this has consequences for animals that live in these oceans, especially the ones that form hard shells and skeletons from particular forms of calcium carbonate minerals. But the whole of the ecosystem can have knock-on consequences from that. Now, I mentioned warming of the ocean a few times. If you think about climate warming, maybe in your mind you have a picture of long-term but relatively slow change as a function of time. In reality, that's not how warming manifests, at least not solely. In the ocean, just like in the atmosphere, there are heat waves. So in the ocean, you have these bursts of very warm water that can exist for a few weeks, maybe a bit longer. But these can be particularly damaging because they can push organisms beyond their limit of resilience, especially if they happen to be coupled with bursts of ocean acidity. And again, we can see this is for a low CO2 future. This is the likelihood of these marine heat waves. It's not good, but it's on a level. But if you move into a high CO2 future, the likelihood of these marine heat waves is very strongly elevated, especially in places like the Arctic, also the tropical ocean. And again, that's hugely damaging to the animals that live there. And moving on to the land just briefly, this is about permafrost. This is the frozen ground. It's at both poles, but it's especially important in the Arctic. And we know that it's thawing. If you happen to see Frozen Planet 2 last night, there was some incredible footage about thawing permafrost in the Arctic. And this really matters because this permafrost stores a lot of greenhouse gases. This permafrost stores a lot of carbon dioxide, especially a lot of methane, which is a very powerful greenhouse gas. And as this permafrost thaws, all these gases are released to the atmosphere and accelerates global warming. It's what's called a positive feedback, which sounds like a nice pat on the back for having done a good job. But in climate terms, that's actually a really bad thing. A better term is a vicious circle, to be honest. Not only is there a global consequence from accelerated global warming, there's also a local consequence, because people live in the Arctic. It's not like the Antarctic, where penguins and crazy scientists go. In the Arctic, there are indigenous communities, there are local communities, and they live there. And if their land is thawing and their way of life requires it to be frozen, then they have to adapt. And if they can't adapt, then they have to move. So there are strong consequences for the people who live in the Arctic. And a really important point, I mentioned earlier, Antarctica is a huge ice sheet covering it, miles thick in the middle. Greenland is another big ice sheet. If all of that ice melted, sea levels would go up hugely around the world. The good news is that all of that ice isn't going to melt, at least not in my lifetime. The bad news is that a lot of it is already melting. Sea levels are already rising because of melt from Antarctica, melt from Greenland, melt from even smaller glaciers that aren't necessarily part of major ice sheets. And we know that this will continue. This is one of the things about climate change that we can be most certain of, is that the sea level rise, including that from Antarctica and Greenland, will continue for the rest of this century and for many centuries beyond. There's nothing we can do about that fact, but we can influence the level at which sea level rises. What these lines here show are different scenarios for different climate change futures. The lowest one here is a relatively benign scenario, and that's where we can constrain our emissions to a level consistent with the Paris Agreement. As we get more and more emissions, you get more and more sea level as a function of time. You could end up with maybe a metre of sea level rise by the end of this century. And that's hugely damaging for low-lying countries, for countries with coastal infrastructure, for island states. It's massively a problem. You can actually put some numbers on this as well. The financial cost of sea level rise in 2100 has been actually calculated. And this was done quite recently. What all these people did was take the scenarios, the projections of sea level rise, and couple that with societal models to try and understand what the cost would be. And with low emissions, which is kind of the best we could hope for, and with optimal adaptation, so people make the best possible preparation they can for sea level rise starting now, the cost would be about $60 billion per year by the end of this century. And that's the best case scenario. The worst case scenario, which involves people taking no actions whatsoever to prepare for sea level rise, is over $1 trillion per year. Huge amount of money. It's potentially even worse than that. The line here, this dashed line, is the one that really scares me. That line relates mainly to Antarctica, and that line relates to the configuration of the Antarctic ice sheet. It's unstable, but these parts of it are unstable. There's a possibility that if you go into a vicious circle that is so strong that major parts of the West Antarctic ice sheet disintegrate much faster than they would otherwise. We don't know that that will happen. We think the chances of that happening are pretty small, but we can't rule it out. And this is why IPCC call it a low likelihood, high impact storyline. Because if we end up on that curve, this $1 trillion per year will be really low. It will be many trillions of dollars per year. And that becomes a very significant part of global GDP. So we have to do everything we can to avoid that line and try and stay on, hopefully, one of these lines. So there's a huge amount of information in these IPCC reports, especially the Ocean and Cryosphere. And what we tried to do was summarise that information in a way that was accessible for policymakers and for anyone else who didn't want to have to sit down and read it all. And the way we tried to summarise it was with this schematic for the Arctic. There's a lot of detail here. What we tried to do was pick out the effects of climate change on the Arctic in terms of, is it a positive effect? Is it mixed or neutral? Is it a negative effect? And we've colour-coded accordingly. So don't worry about all the detail, but you'll be able to see for all the different components of the Arctic system, there's a lot more negatives than there are positives. And that means, the phrase you hear a lot in climate change is, there's winners and losers. And that's true. But there's a lot more losers than there are winners. And that really matters. Some of the winners will have you raising your eyebrows slightly. It says shipping here, which is an industry. Ships go to the Arctic. As the ice melts, more ships can go to the Arctic. And so if you own a shipping company, that's potentially a positive consequence. But if you care about the environment, then having more ships going to the Arctic might seem like a bad thing, with the risk of oil spills, with pollution, with black carbon emissions. So even these positive impacts seem very nuanced at best. This is the comparable schematic for the Antarctic. It's more simple in some ways because there's much less human presence in the Antarctic than there is in the Arctic. Again, there's winners and losers. Quite a lot of losers down here. There's some winners here, you might think, these blues. This relates really to more ocean being exposed to sunlight into the atmosphere. As the sea ice retreats, more of the ocean surface gets lit up by the sun, and that makes it available to grow phytoplankton and for the food chain to move in, whereas before it was covered by ice and that couldn't happen. So if you're a phytoplankton, you might think this is good news. But you have to bear in mind that this apparent positive comes at the cost of losing the cryosphere and all the damage that instills, which we just talked about. So again, there's winners and losers, but even the winners very heavily nuanced in terms of the cost of their win. So there's vastly more detail in the reports. You can perhaps draw out three overarching messages from this sequence of IPCC reports. One is that climate-induced changes in the ocean cryosphere are having significant impacts both locally and globally, and everybody in every place is affected, including us here today. The second point is that across many aspects, the ocean and the cryosphere of the future will appear significantly different from the way they appear today. And there are some things that we just can't stop. However, the good news is that choices are available. It will influence the nature and the magnitude of those changes. We can still take meaningful action that will help minimise climate change, minimise the damage we're doing to the ocean, minimise the loss of the cryosphere and everything that that involves. So I thought I'd give just a few personal thoughts about the process of the IPCC. I'm sure you've seen IPCC mentioned on the television, perhaps seen a few highlights every time the report is produced, but it's a fascinating process to be involved in. This set of numbers just summarises the report that I was involved in. It had over 100 lead authors, of which I was one, from all around the world. It had to be approved by all 195 United Nations countries before it could be signed off. I'll say something about that in a second. We cited 6,981 independent scientific studies in the report, all of which we had to read and understand. Not everyone individually. I didn't read all 6,981, but I did read a lot of them. It certainly felt like a lot of them. And it went through a peer review process in the same way that a scientific paper will go through a peer review process. Except this peer review process was open to anybody. Anyone in the whole world could sign up to be a reviewer, read the report, and comment on it. And there were 3 rounds of that. Many of the comments were very well informed. If you get a chance, which you will, you should sign up and read and comment on IPCC reports. Some of the comments were almost abusive. Some of the comments came clearly from the climate skeptic lobby, who were saying climate change isn't real. Why are you writing a report about it? Every single comment that we received, and there were 31,176 of them, we had to respond to. So we had to write back and say, yes, we agree, we will change the report, or no, we disagree, this is why we don't agree with you, this is why we're not going to change the report. So when you write your next journal paper and you get 20 or 30 journal reviewer comments saying this is okay, publish it, or whatever, spare a thought for us, we had 31,000 of those to work through. It's not a good process. Someone produced this, which made me laugh. It's the IPCC Snakes and Ladders game, which summarises quite accurately, I thought, the actual process. You start down here at the beginning when the governments agree to produce the report, and you think it should be a nice linear process that gets you to the end and the report is published. In practice, of course, at every step there's a snake waiting for you to fall down and go back to where you were 6 months ago or where you were a year ago. And we went through all of these boxes. This is one that I went through. Lead author's spouse threatens divorce. I like to think she was joking when she did that, but she might tell you a different story. We did get there in the end. The report was accepted by the United Nations governments and it was published. And it's a big relief when that happens. Before it gets published, it has to go to United Nations plenary for approval, and the plenary sessions are brutal. You have to get specially trained before you sit in an IPCC plenary so that you know how to respond to the government when they're challenging you. This was the training session. I wasn't really the delegate from Mordor. This is something that my colleagues made, which I think they were commenting on my management style, which is possibly something I should learn from. I think the key thing here is that United Nations government delegations, they bring along some really top scientists. It's not just politicians there. They bring along chief scientists, climate scientists from their leading agencies and so on. They're not actually interested in proving you wrong, for the most part, but they are absolutely adamant that you must prove what you said in the report is correct. And the way you do that is you're in the plenary hall and you go through the whole report, line by line, comment by comment, and anyone from the 195 governments can challenge that comment, and you have to be able to defend it. And if you can't, a line goes through it, and the comment's removed. And that is pretty intimidating. This is the view from the floor. This is a shot I took on my phone. These are all the government delegations up here waiting to pounce, and it feels like a real bear pit. It feels like you're really, really pressured. But you do have to keep reminding yourselves, they want the report too. This is for them. This is not them trying to catch you out. This isn't trial by ordeal. They want the report so they can make the best possible policy. And in the end, you reach compromises, you reach solutions, the report gets published. Sometimes questions get asked, and they are, like I say, very, very good questions. And you have to consult with your colleagues. So all the microphones get turned off, and the scientists go into these panicky huddles, and all the laptops come out, and the scientists say, well, who wrote that bit? And you try and trace it back to the actual primary literature that you base the comment on, the statement on. This is me looking slightly panicked. And it happens a lot. This did a lap of Twitter at the time with the hashtag accidental renaissance. And the best renaissance paper we could find was this one. It seemed to match quite well, actually. But there we go. And it becomes a test of stamina. The approvals plenaries are typically 3 days, but in each day you start at 8 in the morning and then you finish at midnight or later. And when it gets to the final day, and you've only approved half the report, and you've still got the other half to do, you just keep going. And the final session, we started at 8 in the morning, and we finished at 11 o'clock the following morning. And people were just conking out. People were just falling asleep in their chairs. You know, not just the scientists, but government delegations and everybody. And so you have to say, is this really the best way to make climate policy that will, if it's done properly, influence the future of the planet? And the answer is no, this is a terrible way to do it. Everyone is exhausted. But it's like the famous quote about democracy being the worst form of government except for all the others that have been tried. This is the worst way of making climate policy except for all the other ones that have been tried. And at least this one works to a level. Far from perfect, but it works to a level. And we got there, and there's this huge outpouring of relief that you finally got this report you've been working on for 2.5 years over the line. It can be launched, it can then go away and hopefully be part of the government dialogues, become part of the policies that will help put the planet on a better footing going forward. So what now and where next? Well, COP26 happened, you remember that? That was in Glasgow around about this time last year. COP27 is happening next in Egypt. Next month I shall be going. These COP meetings, Conference of Parties meetings, these are where the governments all get together and say, well, how shall we respond to these IPCC reports and the climate crisis that we're currently in? COP26 did a lot of good, but it's certainly not solved the issue. There's much more to be done. We're currently on track for something like 2 or 3 degrees of warming globally, and that's if the COP26 commitments are delivered. That's a big if. The long-term promises that were made might keep us to 1.8 degrees of warming. And those long-term promises are the sort of promises saying we will reach net zero by 2050, but then there's no detail at all of how they're going to get to net zero by 2050. These are promises and they're great to have, but they need to be substantiated. The Paris Agreement, which is the landmark agreement that we're all trying to stick to in terms of climate change. The aspirational target was 1.5 degrees. The target beyond that was trying to keep climate change as much as we can below 2 degrees. There's still a hope of keeping it below 2, just. 1.5 looks pretty unachievable, to be honest. And where we are, we're actually heading for something a bit more than that, between 2 and 3. These sound like small changes, a few tenths of a degree. They sound pretty small. But you've got to see it in perspective. That's the average across the whole world. But climate change won't be evenly distributed across the whole world. One of the areas that we hit hardest is the polar regions. The Arctic especially, Antarctica and the Southern Ocean as well. So a 2-degree warming globally, which is this scenario here, could easily be 4 degrees or 5 degrees in the Arctic. And that's catastrophic for the Arctic. If you go beyond that, if you go up to a nightmare scenario like 4 degrees, you can end up at 7 degrees or more warming in the Arctic, which is almost unthinkable. So we have to care deeply about these few tenths of a degree if you care about the polar regions, because a few tenths of a degree globally can mean a lot more in the Arctic or the Antarctic. So what do? We keep working the process. We have to push for delivery on the commitments made at COP26, and COP27 will be a part of that. We need rapidly increased ambition beyond what is currently on the table, and that means cuts in emissions, it means preparation for the climate change that is happening. It means financial agreements to pay for these things globally, including for developing countries. Many of the countries that will be hardest hit by climate change have the least capacity to deal with it because of their economies. They can't do it by themselves. It's incumbent on everybody, all the other countries that can help as much as they can. And as a scientist, I would argue what we also need is an enhanced understanding of ocean climate change and its impacts. Now, that's obviously me lobbying for what I do, but one of the things we can say with certainty is that the ocean can still spring surprises on us. Remember that dashed line I showed earlier for sea level rise from Antarctica? If Antarctica goes into this vicious circle, we still need to understand that much, much better. That's just one example. We still need to understand it much, much better to understand how far away from that are we, and what action do we need to keep ourselves far away from that as we possibly can. So I'm wrapping up now. You remember at the start I showed you a picture of planet Earth, a picture of our home. This is another picture of planet Earth. This is actually the furthest away picture of planet Earth that's ever been taken. This is from the Voyager spacecraft. It was taken from 4 billion miles away. It just happened to be when Earth was lit up by this sunbeam. It's very famous. It's called the blue dot photo. Pale blue dot photo. To me, it actually really does sum up beautifully how small and how fragile our home is. It's the only one we've got, and we do need to do everything we can to understand it and ultimately to protect it. That obviously includes the ocean and the polar regions, and I would argue it includes especially the oceans and the polar regions because of their global reach, because of how susceptible to climate change they are. I'll stop there just to say thank you to these people who inputted material, and thank you to you all for coming along and giving up your evening to listen to me.